Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed Liouville's theorem. We will continue with that. So let me write Liouville's theorem. For the change in density with time. So this is our today's topic. I will change the color first. So let me use this blue color. So I will write here continued. We will continue with the discussion of the previous lecture. In the previous lecture, we said that corresponding to an ensemble of isolated systems, first we considered an isolated system, which was specified classically by F generalized coordinates and momenta, Q1, Q2, Qf, then P1, P2, up to Pf. So we had an isolated system specified classically by F generalized coordinates and momenta, which I have listed in this set. Then we said and discussed in the statistical ensemble of such systems, there will be a density function which will specify the condition of the ensemble as a whole in phase space. That density function we denoted by rho, and that density function is function of all q's up to qf, all p's up to pf, and in general time also. Then what we did, we first found the number of systems in the ensemble which at time t have positions and momenta in the element of volume dq1, dq2, this is product here, dqf, then dp1, product here, we're multiplying the things up to dpf. As we discussed in the last lecture, this is volume element. Volume element in this phase space. Now, the number of systems in the ensemble of the systems at time t that lie in this volume, that in other words means that have positions and momenta in this element of volume of phase space, which is lying between q1 and q1 plus dq1, q2 and q2 plus dq2, similarly up to pf and pf plus dpf, that number of systems will be simply this density function times this volume element. So if I multiply this density function by this volume element, I will get the number of systems in the ensemble under consideration, which at time t have positions and momenta lying in this element of volume. Then we said that every system in the ensemble, because ensemble is a collection of systems, and every system in the ensemble moves in time according to its classical equations of motion, which are Hamilton's equations of motion. What are those equations? Those equations are, let me write them. Those equations are qi dot is equal to dou h by dou pi, and pi dot is equal to minus dou h by dou qi. In the last lecture, we labeled these equations as equation A. So every system in the ensemble moves in time according to these classical equations of motion. Remember, qi dot is the time derivative of the ith generalized coordinate, and h is the Hamiltonian of the system. Pi dot is the time derivative of ith generalized momentum, and you know it is minus dou h by dou qi. Then when these points in the ensemble move according to these classical equations of motion, what happens as a result of this motion? The density rho of systems in phase space changes in time. Then we were interested in finding dou rho by dou t, partial derivative of this density function with time in the phase space at a fixed point or at a given point of phase space. Then to find it, what we did, we focused our attention on any given fixed element of volume of phase space. That element was this element. We focused attention on this element. Then the number, the change in the number of systems within this volume element of phase space was this volume element times dou rho by dou t times dt. So dou rho by dou t, let me write it, dou rho by dou t times dt, when we multiply this thing by this volume element, which is dq1 up to dpf, when we multiply this thing with this volume element, what we get, this gives me the change in the number of systems within this volume element, which is my volume of interest, in time dt. Then we said this change in the number of systems of elements existing in this volume element is due to the number of systems entering and leaving this volume in time dt, right? Then we found that number by focusing our attention on the number of systems entering and leaving the volume through two phases. We consider two-dimensional situation. The one phase was q1 is equal to constant, and second phase was q1 plus dq1 is equal to constant. So when we found the net number of systems entering that two-dimensional rectangle, I should say, when we talked about that, actually it was net number of systems entering the whole volume element, but we considered only first two phases, that is q1 is equal to constant phase and q1 plus dq1 is equal to constant phase. Then we summed over all the faces of the volume element, and we obtained an expression for d rho by, sorry, dou rho by dou t. So let me list those equations so that we can connect to the today's lecture. So there were some equations which we named. One equation which we wrote was this one. Dou rho by dou t is equal to minus summation I is equal to 1 to f dou by dou qi of rho dou I dot plus dou by dou pi of rho pi dot. This equation we named as equation 1. So first we obtained this equation for dou rho by dou t minus I to f summation of dou by dou qi rho qi dot plus dou by dou pi of rho pi dot. This is dot here, right? Then this equation we wrote as, let me write that equation also. Let me change the color of my pen to distinguish the equations. So we wrote another equation for this where we used the product rule. We wrote dou rho by dou t is equal to summation I is equal to 1 to f. This is here negative. Then inside the bracket, I have dou rho by dou qi dot plus dou rho by dou pi dot plus rho times dou by dou qi of qi dot plus dou by dou pi of pi dot. We have already discussed this result in the last lecture. I'm just connecting it with today's lecture. It's minus I to f dou rho by dou qi dot plus dou rho by dou pi dot plus rho dou by dou qi dot plus dou by dou pi dot. We have just what we did actually, we have used product rule here. We have used product rule here and product rule here. So we got overall 4 terms in our sum. Then what we did, we named this equation as 2, right? Then we used equations A, that is Hamilton's equations of motion, into, first we used that independently. Let me write that equation also. Let me write it. So by virtue of equations A, we wrote by virtue of equations of motion A, the equations labeled by A, it follows that dou by dou qi of qi dot plus dou by dou pi dot is equal to second order derivative of Hamiltonian dou qi dou pi minus second order derivative of Hamiltonian of the system dou pi dou qi, which we argued that this is equal to 0, and we named this equation as 3. What was the argument? Argument was that Hamiltonian of the system is state function. So whether you find it a second order derivative first with respect to, you differentiate first h with respect to p I, then qi, or first qi, then pi, these second order derivatives will be equal. Therefore, this difference is 0. How we obtain the second order derivatives? We use it the Hamiltonian equation, because when we find dou by dou qi of qi dot itself is what? That is dou h by the previous page, dou h by dou pi. So dou by dou qi of qi dot is dou by dou qi of dou h by dou pi. That is the first term. And negative comes from this second thing, where dou by dou pi of pi dot according to Hamilton's equations minus dou h by dou qi. So we reach it here, right? Then what we did, we used this equation 3 in 2. When we do that, this term in the sum, that is this term in the sum becomes 0, right? So let me write. So using 3, equation 2 reduces to. Let me write. Let me change the color again. It's brown now. So using equation 3, equation 2 reduces to, it reduces to this dou rho by dou t is equal to minus summation I is equal to 1 to f. Then we have inside the bracket dou by dou qi rho qi dot plus dou by dou pi of rho pi dot. We named it equation 4 in the last lecture. Here we stopped in the last lecture. Then we will move today forward. Now we will move today forward. So it is minus summation I to f dou by dou qi rho of qi dot plus dou by dou pi of rho pi dot. So this equation 4 gives me what? It gives me the value, how this rho density function changes in time, but at a fixed point in phase space. Because it is partial derivative of rho with time. Rho is depending not just on time, it is depending on all q's and all p's, right? So this is giving me the rate of change. Let me write it clearly. So this is giving me now the rate of change of rho with time at a fixed point in phase space at a given point in phase space, right? So remember why this change is rho with time at a given point, because corresponding to the ensemble of systems, there is some density function which describes it a situation at a particular time. But what happens? The individual systems in the ensemble, which are points in the cloud, they move according to classical equations of motion, Hamilton's equations of motion. That leads to change in rho with time. We were interested in finding that, and we have found that using this equation 4. The equation 4 gives us that rate of change. Now, we want to find the total derivative of rho with time. So what will be that? Let me write it first. Or equivalently, we can write, change the color to distinguish the equation. Equivalently, I write this d rho by dt. Now it is d rho by dt, understand it. It is now the total derivative of density function with time. What it will be, it will have two parts. One, rate of change of rho with time when point is fixed, plus the portion of the change in rho due to the motion of point if we move the point in phase space. We don't keep the point in the phase space fixed, right? What is that term? Let me write, I will justify that. It is summation I equal to 1 to f. Then I have dou rho by dou qi dot plus dou rho by dou pi dot. Right? Now think about it first. This is the variation of rho with time when point is fixed. This is the variation in rho when Q's and P's are changing in time. Q's and P's are changing in time. That means points are moving with time. See, what is this first term in the sum? It is dou rho by dou qi dot. Qi dot is the time derivative of qi. In this term, actually, if you think about it, we are using the chain rule. We want to see how rho changes with the change in qi, but qi itself changes with time. So I am finding the change of rho with respect to a change in qi using chain rule. I am writing dou rho by dou qi times qi dot. Qi dot is time rate of change of Qi. So that means I am multiplying these two changes to see how rho changes with Qi. It is here chain rule in action. Now rho changes also with P's. So how it changes with Pi? Same, we do the same chain rule usage. We find its change with respect to Pi and multiply it by the change in the Pi with time, right? I will give an assignment. Think about this. So I am saying rho is function of all Q's and P's and time. First term, which is the partial of rho with respect to time, gives it its rate of change where time if point is fixed. Because if point is fixed, this second term, this term is zero. Point fixed means Qi dot is zero, Pi dot is zero, both terms will vanish. Q's are not, P's are not changing with time. But when the point of observation is moving, we are moving with the point. There are two things. One thing is we are seeing the variation rate of change of rho with time at a particular fixed point in phase space. Second thing, we are not fixing our point, we are moving with the points. If we move with the point and find the rate of change of rho with time, then this is our quantity of interest, the total derivative of rho with time. So this, let me encircle it. This is giving me the rate of change of rho with time when I move along with that point, the point at which I am finding the rate of change of rho with time. Now compare this equation with equation 4. Let me use another color. I will use here black. Now this thing, pen is not working properly, so I have to make adjustments. Bear with me. So this thing and compare with this. It's the same thing, but opposite sign. What does that mean? That means if I use equation 4, we substitute for the partial derivative of rho with time, my total derivative of rho with time will become 0. So let me write it here. This is equal to 0. So this is equal to 0 and I name it equation 5, right? Let me write it where so that you don't get confused. Where d rho by dt as the total derivative of rho with time is measures the rate of change, of rho if one moved along in phase space with the point representing a system in the ensemble of systems, right? Right. So what does it say? It says that this total derivative is 0, right? Now, let me write it another equation, or I should first give it name. Now, these relations 4 or 5, 4 or 5 are both versions of Liouville's theorem. Let me first write it. Equations 4 and 5, equations 4 and 5 are known as Liouville's, it is pronounced and Liouville's theorem. What's the difference between the two? Both are Liouville's theorem. Difference is only one thing. In equation 4, you are finding the rate of change of rho with time at a given point in phase space. Your point in phase space is fixed. In 5, you are expressing this rate of change of rho with time, but you are not fixing the point. You are moving along with the point representing a system in the system of ensemble of systems, right? So this equation 5 says this rho is conserved in time. Its total derivative is 0. So this equation 5 is called or named as principle of conservation. Let me write equation 5, which is the form of Liouville's theorem. It is called principle of conservation of density in phase space. Density in phase space. Try to understand it, what it says. It says, suppose we have some ensemble of systems, first, and our system or in interest for which we have established or conceptualized an ensemble of system. That system in question or system of interest is isolated system, right? With f generalized coordinates and momenta specified by f generalized coordinates and momenta. Let me start from the start. We considered an isolated system which was specified classically by f generalized coordinates and momenta. Then we conceptualized the ensemble of systems of this system of interest and talked about the specification of that ensemble in the phase space by density function, then argued that each individual points, that means each individual systems in the ensemble of systems, move in time according to our Hamilton's equations of motion, and we reach it here, equation 5. So it says this rho will be conserved in time. That means if you imagine that there is an cloud of points representing ensemble of systems pertaining to an isolated system in phase space, now you select some representative point. A representative point is representing one of the systems in the ensemble, and you move with that point in the phase space. You follow that point in the phase space. What you observe in your neighborhood, there will be no variation in density with time. This is the meaning of equation 5. I repeat, if you select one of the points in the cloud representing ensemble of systems pertaining to a system which is isolated, right? So if you move along with a point in the cloud, you will not notice in your neighborhood that there is variation in density. It is in the neighborhood because we are taking only first order changes. We are taking only first order derivatives into consideration, right? So I hope it is clear. Now there is another form we can express these results in another forms. We will discuss now them. So let us move. Let me edit this page. See by equations of motion, that is Hamilton's equations of motion. Equations of motion, which we labeled as A, one can write equation 4 as I can write this way: dou rho by dou t is equal to minus summation I is equal to 1 to f. Then I have dou rho by dou qi dou h by dou pi minus dou rho by dou pi dou h by dou qi. Let me name it equation 6. What we have done, we have used equation A to rewrite equation 4 as, let me check it first, dou rho by dou t is equal to minus summation I to f, dou rho by dou qi, dou h by dou pi minus dou rho by dou pi, dou h by dou qi. Let me move to previous page. Understand it, what we have done. This is our equation 4. So here I replace it qi dot by dou h by dou pi. These are my equations of motion. I replace it qi dot by dou h by dou pi, and I can replace pi dot by dou h by dou qi. So we have done that in 4. This is my 4. So I replace pi dot by minus dou h by dou qi and qi dot by dou h by dou pi. So I got this equation 6. This minus is because pi dot is minus dou h by dou qi. C. Now what we do, we define a thing. There's a definition here which we use to understand why I have written equation 4 in this form. I will use first another color. Let me use green. We define an object in classical mechanics that's called a Poisson bracket. So let me first clear that, then you will understand equation 6. Poisson bracket definition. What it says, see what it says. For any two functions m and n of the coordinates and momenta of the coordinates and momenta of a system the Poisson bracket right here, the Poisson bracket is denoted by this curly brackets, then we write M comma N, is defined let me correct my pen, is defined by, I will change the color to write this definition of Poisson bracket, write in red, Poisson bracket Poisson bracket of M and N is by definition summation I dou M by dou Qi dou N by dou Pi minus dou N by dou Qi dou M by dou Pi. So this is, it is understood why the summation is taken over all the degrees of freedom of the system. So let me check it, then I will explain it. It is actually self-explanatory. Still, I will explain it. So how we define Poisson bracket? We have some system and which is having f degrees of freedom, which is specified by generalized coordinates and generalized momenta. Then there are two functions, m and n. They are functions of coordinates and momenta of the system. Then the Poisson bracket, which is written in curly brackets, defined, this is the notation, curly brackets m comma n. So that means when I write Poisson bracket of two functions, it is understood this is this summation, this right hand side, right? This thing. To understand it, this is not clear, this line. Let me make it clear. So when I write Poisson bracket of m and n, this is this sum. So what we do in this Poisson bracket, you first find derivative of m with qi, then multiply it by derivative of n by pi, then you subtract. In my negative term, you do the reverse. You find the partial of n with qi and partial of m with pi. Then you sum over all the degrees of freedom. This whole sum is in compact form. This whole sum in this compact form is written Poisson bracket of m and n. Now, why this has been defined? Because in classical mechanics, if you see this equation 6, such sums, such expressions appear most of the times, or I should say, in many situations, such expressions appear. If you see this equation 6, if we use the definition of Poisson bracket, can be in compact form written as minus times the Poisson bracket of rho and h. So this is how things become compact. So let me write that. So using equations, this definition of Poisson bracket, equation 6 can be written as, it can be written as dou rho by dou t. We sometimes write it this way. That's q comma p in the subscript is minus times the Poisson bracket of rho and h. Let me name this equation as equation 7. So this is this subscript qp means the point is fixed. So this is also how we express Liouville's theorem, right? I think I should stop here. There is another way we can express the Liouville's theorem, but that we will discuss in next lecture. Now, before stopping, let me summarize now. So, if we have an isolated system characterized by F generalized coordinates and generalized momenta, F generalized momenta, that means it is having F degrees of freedom, then we can conceptualize an ensemble of systems, of such systems, and the situation of that ensemble in the phase space will be described by density function. Then we said that each point, that each system means each point in the ensemble will move according to Hamilton's equations of motion that will lead to change in density with time. So we showed that the partial derivative of rho with time, that is equation 4, which is one form of Liouville's theorem, is given by this sum, which is given in this equation 4. Then another form of Liouville's theorem, which we write in the form of total derivative, is equation 5, which is 0, which we named as principle of conservation of density in phase space. It simply says that if you move along in phase space with some point representing a system in the ensemble, you will not see any change in the density with time. That is, rho is conserved in time. It is, of course, in the neighborhood of that particular point. So this another form. Then we wrote this partial derivative of rho with time using the definition of Poisson bracket. So I hope it's clear. Go through all the lectures. Don't miss a lecture. And if you have any queries, questions, you can comment in the lecture. You don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.